Welcome to Fundamentals of Computers lecture series. This is the second session, and in this session we will have a look at binary numbering system and ASCII table. The objective of this session is to understand why we need to learn binary numbering system in order to understand the programming. We will introduce binary numbering system and its relationship with decimal and hexadecimal numbering system. We will see how binary numbers can be converted into hexadecimal and vice versa. We will look at the arithmetic and logic operations on binary numbers. Finally, we will see how the characters be represented using the binary numbering system. Let us start with the binary numbering system. Why do we need to learn the binary numbering system? Computers are electronic circuits that operate on the binary values. Some of the examples where the binary comes into the play in the computers are when the charge is stored in a device, then we say that it can provide the current and that represents the value of 1. When the charge is missing, the electric circuit cannot be used and that represents a value of 0 in the computers. Another example is the flowing of the charge. If the current can flow through the circuit, then we say that it's a value of 1. And even when the charge is available, but somehow we can stop the flow of the current, that is represented by a value of 0. Example of this is turning off the switch of some device. In the computers, the circuits that exist in the computer have the switches at the back end that can be turned off, and that stops that specific circuit from working even if the electricity is being supplied to the computer. Another more accurate description of the binary numbering system in the computers is the edge transition. In a single digital cycle, there are two edge transitions. One is a negative edge transition and the other one is a positive edge transition. A negative edge transition in the computers is equivalent to 0 and a positive edge transition in the computers is equivalent to 1 value. Based on this description, the computers will only be operating as zeros and ones, and anything that we want our computers to perform, we have to convert that information. Anything that we want our computers to understand, we have to convert that information into binary for us to be able to get something useful out of our computers. In order to understand the binary numbering system, let's first have a look at a very familiar numbering system that we use in our daily life, and its decimal numbering system. Then we will draw the comparison between two for better understanding of binary numbering system. In the decimal numbering system, there are 10 digits which are 0, 1, 2 up to 9. Combination of digits makes numbers. For example, 102 is a combination of 3 digits 1, 0 and 2. Each number has a value which is decided based upon the position of the digits. The number 102 has the value of 102, which is derived as the value of digit 2 is 1, so we multiply the digit with its value. The value of digit 0 is 10 and the value of digit 1 is 100. How do we get these values? The least significant digit here is 2 and its value is always 1, which is actually coming from 10 raised to the power 0. For every subsequent digit on the left hand side, the value is increased by 10 because it's a decimal numbering system. So this is 1 multiplied by 10, and that gives you 10 raised to the power 1. The next value is once again increased by 10, so it becomes 10 multiplied by 10, and that is 10 raised to the power 2, or simply 10 raised to the power 2. So if we continue on this trend, if there was another digit, its value will be 10 raised to the power 3, which is 1000, and so on. The value of entire number is the sum of the individual digit values. So this number 1 or 2 is 100 plus 0 plus 2, which is 102, and that is why we pronounce it as 102, or on the similar lines 1102, and so on. Now let's have a look at binary numbering system and draw the comparison. In the binary numbering system, there are two digits. The digits of the binary numbering system are called bits, and this is the term that we will use from now onwards. The two digits are 0 and 1. Similar to decimal numbering system, in the binary numbering system, we create the numbers by combining the digits of the binary numbering system. Because there are two digits of 0 and 1, therefore the numbers of binary numbering system will be a combination of zeros and ones. For example, 1, 0, 1. Similar to the decimal numbering system, the value of the number is drawn by the value of the individual digits multiplied by the value of the respective position. So, just like the decimal numbering system, the value of the rightmost digit, which now will be called LSB, standing for least significant bit, will be 1, and it's called least significant because its value is least among all the digits. Similarly, the leftmost digit is called MSB, which stands for most significant bit. So value of rightmost digit is 1, so we multiply the digit with the value. The next digit has a value of 2, so we multiply the digit with the value. The next digit has the value which is 2 times the value of the previous digit, so its value becomes 4, and the digit itself is 1. Here, compared to decimal numbering system, we are increasing the value of each digit by a multiplier of 2. So this is 2 raised to the power 0, which is equal to 1. The next digit has a value of 2 raised to the power 1, which is equal to 2. The next digit on the left hand side has a value of 2 raised to the power 2, which is equal to 4. If there was another digit on the left hand side, its value will be 2 raised to the power 3, and so on. Therefore, the value of binary number 101 is 4 plus 0 plus 1, which is equal to 5. Similar to binary numbering system, there is another numbering system called hexadecimal numbering system. I will not cover all the details here, but hexadecimal numbering system has 6 more digits in addition to the 10 digits of the binary, and their values are equal to 10, 11, all the way up to 15. Once again, the numbers are created by combinations of these digits, and this looks a little strange because of the alpha characters inside the numeric characters, but that's how the hexadecimal numbers are written. The value of the number is derived from the value of individual digits. Here, instead of using 10 or 2, we use 16 as the multiplier for the value. The rest remains the same. Why do we have a look at the hexadecimal numbers? We basically want to perform the conversions between binary and hexadecimal numbers. And why do we want to perform the conversion between binary and hexadecimal numbers? Because the binary numbers are long strings of zeros and ones, which are very difficult to write. There are high chances of mistake. We can miss the digits, or we can count a single digit multiple times, and that can result in wrong representation, wrong value of the number. And the binary numbers obviously are not very easily readable by the humans. Therefore, although the computer always operates on the binary numbers, for our ease, for human ease, when we have to write the equivalent of the binary, we write the hexadecimal equivalent, and that is why the conversion between the binary and hexadecimal comes into play. Why don't we use decimal equivalents? Because we will see in a while, conversion from binary to hexadecimal and hexadecimal to binary is always very easy, and therefore we use hexadecimal equivalents instead of using decimal equivalents. So how is a binary number converted into hexadecimal number? We split the binary number into group of 4s starting from the right side, starting from the LSB side. So let's solve an example as we go on. So suppose I have this number 1 0 1 1 1 0 1. It's a binary number. I want to convert this binary number into hexadecimal. So what will I do? I will split it into groups of 4 starting from LSB side. So I'll get 1 0 1 1. This is my first group of 4, and my second group of 4 is 1 0 1. Okay, so these 3 bits have come over here, these 4 bits have come over here. Next, we want to convert each group into its equivalent hexadecimal number. Okay, so how do we do that? This needs a little bit of practice to understand, but find the value of this number and find the value of this number separately. So if I have to find the value of 1 1 0 1, it will be 1 multiplied by 2 power 3 plus 1 multiplied by 2 power 2 plus 0 multiplied by 2 power 1 plus 1 multiplied by 2 power 0, which is equal to 8 plus 4 plus 0 plus 1, and this number is 13. So on the hexadecimal side, I'll try to find which digit represents 13. Okay, so if I am not mistaken, it is E. So this binary number is equal to E in the hexadecimal. Similarly, this one, its value is 5, and that is equal to 5 in hexadecimal. So once I have converted each group into equivalent hexadecimal number, then I can merge the result, and that will be my actual result. So my actual result in hexadecimal will be 5E. So this binary number here is equal to this hexadecimal number. Similarly, we can convert a hexadecimal number into its equivalent binary number. So let's suppose we want to perform the conversion for the hexadecimal number A3. So I have added a 0x in the beginning, which is the way of writing the hexadecimal numbers. It represents that the number after this 0x is a hexadecimal number. So if we have to perform this conversion, we perform each digit, we convert each digit into its equivalent binary. So we have to convert A into its binary, and we have to convert 3 into its binary. There is a procedure for converting the hexadecimal numbers into their equivalent binary value. That is not the purpose of this session, and you don't need to memorize and understand all of that procedure. You can do that for your own interest. So I will skip that procedure. For the time being, you can just use the calculator to get the equivalent values. Later on, you will remember the, say, 16 values. So this digit, hexadecimal digit A, its equivalent binary is 1010, whereas the equivalent binary for hexadecimal digit 3 is 11. Next, if the binary equivalent is less than 4 digits for any specific hexadecimal digit, then add zeros on the left side to make each conversion having 4 digits. So I'll start with this digit, hexadecimal digit 3. I converted it into its binary and I have got 2 digits in the binary. So I will extend it to 4 digits right here. So there should be 2 more zeros added here so that it becomes 4 digits. The second digit that I converted was A. A already has, its equivalent binary already has 4 digits. So I do not need to add additional digits. So any digit that will be short of the 4 digits in the equivalent binary, we will append on the left hand side, not on the right hand side. On the left hand side, we will append zeros to make it a 4-digit number, the way I did for 3. And therefore, my equivalent number is the concatenation of the two binary values. So the number becomes 1 0 1 0 0 0 1 1. So this is the equivalent binary of hexadecimal number A3. We will now have a look at some of the arithmetic and logic operations that can be performed on the binary numbers and that are frequently used in the programming and that will be required for a better understanding of computers. The arithmetic operations on the binary numbers are simple. These consist of addition, subtraction, multiplication, and division. Their procedures are similar to the decimal number procedures, so I'll not go through these details. Generally, understanding the procedures is not required for the programming, and we can use calculator to perform those computations. So I'll skip this portion, but I'll just show one example to draw the equivalence between binary and decimal numbers. So if I want to add the binary number 1011 in the binary number 1001, then the addition of 1 and 1 generates a 1 0, where, so this is a little bit different here. 0 is the quotient and 1 goes as a carry. Then 1 and 1 gets added to produce another 0 and 1 goes as carry. Then the addition of 1 0 and 0 produces a 1 with no carry. Then the addition of 1 and 1 produces 1 0. So this learning the procedure is not required, so I'll skip this portion and move on to the logical operations. There are 4 basic logical operations: AND, OR, NOT, and exclusive OR. And then there are some derived logical operations. We will have a look at those derived logical operations in the next session, specifically the NAND operation. For the time being, we will look at these 4 operations. All the logical operations are performed bitwise. This means that there is no carry in the logical operations and every bit pair of the two numbers is treated individually. The logical AND operator works like this. If I have 2 bits with a value of 1 and 1, then my result will be 1. In all other combinations, my result will be 0. This is something that we use in our real life. An example is if school is open, or it's a school day and teacher is available, then we will have class. Notice that if one of these two conditions fails, then we cannot have a class. If it is not a school day, even if the teacher is available, we cannot have a class in the school. If if it is a school day, but teacher is not available, then we cannot have a class session. Okay, so both the conditions must be true for us to get a positive result, and that is the AND operation. On the similar lines, but with the different results, we have OR logical operator. So the OR logical operator works slightly differently. If both the conditions are true, we get a positive result. However, if one of the conditions is true, even then we get a positive result. On the other hand, if both the conditions are false, then we cannot get a positive result. Example of daily life, or if you go to the market, bring X. Or if I go to the market, bring X. Okay, so the thing that we are trying to bring from the market, if you go to the market, that thing will come to the home. We'll be able to get it. If I go to the market, I'll be able to get that thing. We will be able to get that thing. If both of us go to the market, even then we will be able to get the item, although the quantity will be more than our requirement. However, if none of us goes, then we will have a zero result. We will not be able to get that item. Okay, so this is the OR operation. If only one of the two conditions is met, then our ultimate objective is achieved. NOT operation is very simple. It's a negation operation. If there is a zero value, then its negation will be a one value. If there is a one value, its negation will be a zero value. Exclusive OR operation is close to OR operation, but there is a clause of exclusivity, which means that in our example, when I said that if I go to the market as well as you go to the market, then our objective of buying exactly one item will not be achieved. We will get two items, one purchased by me and the second item purchased by you. And that condition here is considered as a failure. Okay, so exactly one person has to do that task. Okay, so if you go to the market and I go to the market, then our result is not achieved, which is bringing only one item. If I go to the market, I have a one value and you have a zero value, you did not go to the market, then we will get one item. If I did not go and you went to the market, we will get exactly one item. If I didn't go to the market and you didn't go to the market, we will not be able to get the item. So this is an exclusive OR operation. Out of all the values, there should be only one true value or one value, and all other values should be zero. These tables, small tables that I have written over here, they are called truth tables, and in the understanding of the computer, this is an important aspect. We need to write the truth tables of the logical entities that we create, the logical statements that we create. I will show you a relatively bigger example where we perform AND or OR operation on multiple bits. Before I go for that, there is an entity known as logical gates. Logical gates are electronic circuits that can perform the logical operations. We will see the gates and how we can combine multiple gates to form the computer operations, and that is what makes the basis of the computers. So this we will append for the next session. How do we perform the multiple bit logical operations? Here is an example. If I want to perform an AND operation of this value, something that I wrote for the addition as well. So now I want to perform an AND operation. So 1 and 1 bit, just perform the bitwise operation. So 1 and 1 here is 1, 0 and 1 and 0 is 0, 0 and 0 is 0, and then 1 and 1 is 1. So this is the result of 1011 and 1001. The result will be 1001. Similarly, if I want to perform the OR operation on same numbers, and I want to perform logical OR operation, instead of using the bar, I will write OR here for clear distinction between 1 and bar. So 1 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0, and 1 or 1 is 1. So this will be the result of logical OR operation. So note that multiple bit logical operation is just equivalent to performing the bitwise operation on each of the pair of bits. The last part of today's session is binary representation of character set. The character set is basically the set of symbols that you see on your keyboard. This consists of the basic symbols that we see plus the extended characters that we can type, that we want to type on the computers, but they are not directly available on some of the keyboards. Why we need to create the binary representation of the character set? It's because the characters that we see, alphanumeric characters or the symbols that we see, are human understandable and human readable characters. However, computers only work on binaries. Computers only operate on binary values. Therefore, for the computers to understand the characters and the symbols that we want to use, there has to be an equivalent binary value that we as humans understand that if this binary value is added into the computer, that effectively means a specific symbol or a specific character. So what can be a possible equivalence? We already know that there are these digits. 1 starting from 0 is represented as binary value 0. Digit 1 is binary value 1. I can continue until digit 9, which will be binary value 1001. Then we also know from hexadecimal characters that hexadecimal digit A can be represented as 1010, and so on until we reach the digit F, which is represented as 1111. So what about G? What about lowercase a? How do we represent these characters? So maybe I can say and I can derive that this will be represented as 1000. This maybe will be represented as 1010, something like this. Okay, so what is the possibility that this derivation that I have written over here will match with the derivation of another computer where I want to transfer my data? So if I have used this representation for G and someone else has used the same representation for, let's say, K, then when I will transfer my data to that specific computer, my G's will become K's on the specific computer. Therefore, we need to agree on these representations. And that is where the standards come in. Previously, the standard was ASCII, which was limited to alphanumeric characters and the well-known symbols. Now that has been extended to Unicode, which is the superset of the ASCII, and it consists of the characters from the other languages, including, let's say, Urdu, Chinese, Arabic language, and so on. So it covers a vast set of symbols, and it is more or less a standard for representing the symbols into binary values. So it's a single agreed upon representation which ensures interoperability. The ASCII tables, which show the characters or symbols along with their binary values, are available for reference. You don't need to learn these symbols, their binary values on your own. You can just refer to the table whenever you need a conversion. And generally, Unicode is not what you always need. There are very rare cases where Unicode is needed. So an ASCII table can be handy in the case you want to use you want to work with a character set. So ASCII table looks something like this. Here, we will not be very much concerned with the with the decimal value, although knowing the decimal value helps. The main value here is the binary. So for example, if we look at the character A, the agreed upon binary value of this character is 0100000001. Okay, and that is in hexadecimal, this value is 41. Similarly, agreed upon value of lowercase a, this is uppercase a, so lowercase a is 011000001, and its hexadecimal value is 61. So similarly, you can have a look at other possible characters, and this is how the equivalent varies. So whenever I type letter A, capital A, on my keyboard, in the computer, the value that is transferred from the keyboard to the computer's processor is 01000001. Okay, and similarly, whenever I type lowercase a from my keyboard, the value that is transferred from the keyboard to the processor is 011000001. Okay, so this is how the character set works. Whenever the computer will be dealing, it will be dealing with those binary numbers. And whenever we humans will be looking at, we will be looking at the equivalent ASCII value. Okay, this table comes from the website. The source is given at the bottom, and it has a copyright license on it. The next session will be about logic gates and how the combination of the logic gates can be used to create computer operations that the computer performs for us. This session comes to an end. Please consider supporting us on Patreon. Thank you for your attention and have a nice day.